Here we see water splashing out of a plastic jerry can onto coarse building sand at a Kampala construction site. The water flows and spreads, while the sand remains rigidly in place. Just a few feet away, the copper inside these electrical wires easily carries a deadly current, while the thin plastic coating wrapped around it completely blocks that exact same charge. All of these materials are sitting in the exact same environment, exposed to the exact same conditions. So why do they behave completely differently? The answer lies beneath what we can see. Every substance has a microscopic internal structure, a strict geometric blueprint that dictates exactly how it will interact with heat, force, and electricity. Understanding these unseen chemical architectures is how engineers know which materials will hold up a roof and which ones will melt in the sun. This diagram maps out the 4 primary structural blueprints of matter: simple molecular, giant ionic, metallic, and giant covalent. Let's start by looking at simple molecular structures. If you've ever watched candle wax or cooking oil melt on a warm day, you've seen this blueprint in action. In this diagram, you can see these small, distinct molecules are held together by intermolecular forces. Think of these forces like weak magnets. It takes very little thermal energy to break them apart and turn the solid into a liquid. Compare that to the giant ionic blueprint shown here. Materials like everyday table salt are built from a vast, repeating 3D arrangement of positively and negatively charged ions locked tightly together. These giant ionic structures are held by intense electrostatic attraction. To melt these bonds, you need massive amounts of industrial-level heat, like you see at facilities with these massive smokestacks. This rigid lattice also explains how they handle electricity. In a solid state, the charged ions are locked in place, like students forced to sit at their desks. If an electrical charge tries to pass, it simply bounces off. But if you melt the salt, the lattice breaks apart, and freely floating ions successfully carry a bright electrical current. By testing how much heat it takes to melt a substance, and whether it conducts electricity, you can deduce exactly how its internal atoms are arranged. We can apply that same logic to the metallic blueprint. This is the structure behind the iron roofing sheets and copper wires used across Uganda. As you can see in this model, metals form a regular grid of positive ions, completely submerged within a dynamic sea of delocalized, freely moving electrons. This fluid electron sea acts as a high-speed highway for electrical currents. It also allows the rigid layers of metal ions to slide past one another without shattering when hammered or bent. The final structural category is the giant covalent blueprint. Here, massive networks of atoms are continuously joined by incredibly strong covalent bonds, with no separate molecules at all. To see how critical geometry is in these covalent structures, we can look at 2 allotropes, diamond and graphite. Both materials are made of 100% pure carbon. This diagram illustrates diamond's extreme hardness. It uses a 3D tetrahedral scaffold, meaning every carbon atom is bonded to 4 others, pulling rigidly so nothing shifts. By contrast, graphite arranges its carbon atoms into flat sheets held by weak forces, allowing the layers to easily slide off one another onto paper. 2 materials made of the exact same carbon atoms behave in completely opposite ways, dictated entirely by the geometric architecture of their bonds. This table is our diagnostic framework. By mapping melting point and conductivity, we identify substances. If an unknown solid bends easily and conducts electricity, which blueprint is it? The answer is metallic. This physically confirms the hidden presence of a delocalized electron sea. We map out these chemical properties because this is how we safely engineer the physical world around us, from the pipes in our walls to the steel frames in our skyscrapers. A material's internal structure is its permanent personality. Once you can decode that hidden architecture, you know exactly how to build with it.